Hello everyone. In this lectures, I'm going to introduce one of the fundamental equations in electromagnetism, Gauss Law. First of all, I'd like to explain what is flux. Second topic is Gauss Law. Last topic is application of Gauss Law. First topic is what is flux. Mass flux is a rate of mass flow through an area. To understand the flux, we could consider the water is flowing out garden force. How much water is flowing out of a garden force per unit time? That is a flux. Then we can consider the hose, garden force. Cross sections of the garden force, sigma, is the cross sections of a hose. And then if you take a length of the V is the speed of the waters in this volume can move out of the force by unit times. How much water is flowing out per unit time is expressed. Sigma V is a volume. If you take a density, you can calculate how much water is flowing out per unit times. So we call that this is flux. The mass flux, meaning the rate of the mass flow through areas. So if you consider the area of A, as I explained, we could consider the height is V. Then volume can be calculated. This volume is A times V. This is the volume. Then multiply the density of the law, you can find the mass flux. Then flux through an inclined surface. Now we could consider also garden hose, but now inclined cross section. Then water is flowing out of a hose. Even if the edge of a hose has an inclined cross sections, the flux is the same. So total amount of the volume flowing out of this hose can be calculated, this V. Then how can you calculate these volumes? You can take a cross section this way. Volume of the red figures and also the volume of the blue ones exactly same. So we could calculate the volume of the red ones with the volume of the blue cylinders. Area of A times cosine theta correspond to this is A cosine theta. This corresponds to the blue cylinders. A cosine theta times height is a V. So to calculate the mass flux, you can calculate VA cosine theta corresponds to the volume times the density, rho. So VA cosine theta can be expressed with the scalar product of the V dot A. This is scalar product. Okay, so you can take a scalar product of A and V. But in this case, we have to define the direction of A. Direction of A is perpendicular with respect to the areas. Then take a scalar product of the A and the V. This is the velocity V. You could calculate a V dot A becomes a VA cosine theta. So to calculate the flux, you need to calculate the scalar product of V dot A. Using the same method, we'd like to calculate electric flux. So I introduced the area vector of A is perpendicular to the area we considered. And if the electric field is directed in these directions, you need to take a scalar product of the A and the E. So electric flux is defined with these equations, scalar product of E and A. And direction of the area vectors, if you consider the plane areas, then area vector can be taken in these directions or opposite directions. So it's up to you how to take a direction of A. But for a closed surface, area vector is always directed to be outward. This is the area vectors. Zero electric flux. If there is no electric field, then electric flux becomes zero boundary. And if you consider the uniform electric field, this electric field is uniform. Then if you consider the two positions, this is the area vector of A. This is the area vector of A. Scalar product E dot A. This is E dot A. So this green part is cancelled out with the blue part, because this part is E dot A becomes E A cosine pi minus theta. This becomes minus EA cosine theta. For the green part, is this going to be theta. So it becomes EA cosine theta. So if you sum up these two, it becomes zero. Cancel out. So if you consider the uniform electric field, flux becomes zero. Then we would like to consider the surface, small surface area of a sphere. Radius of a sphere we consider the R. Then we would like to consider the small surface area of a sphere. Then I'd like to explain the coordinate. So in the Cartesian coordinate, we use the x, y, z coordinate. In the spherical coordinate, to express the positions in a three-dimensional space, instead of x, y, z, we use r. R is a distance from the origin, and theta is the angle, and phi, you can find the projections of the point onto the xy planes. Then draw the lines connecting the origin to the projected point. Then find out the angle of this is phi. So to describe this point, you could use the xyz. Also, you could use the r theta phi. This is one of the methods to describe the positions in the 3D space. Then we'd like to express the surface area of a sphere. Take a really small angle of the thetas. This is small angle of the d thetas. Then you can calculate. This length is expressed r d thetas. Also, you could consider the circle. So in this case, the radius of the circle is expressed r sine theta. You could consider the small change of the angle d phi, because this is phi, this is d phi. Then you could consider that this length can be expressed r sine theta d phi. We'd like to create a small areas on the surface of a spheres can be calculated. This times this one. So area is calculated r d theta times r sine theta d phi. So area is expressed r squared sine theta d theta d phi. So we use this is a ds. So this is correspond magnitude of the area vector of this small area can be expressed r squared sine theta d phi. You might wonder, maybe we could calculate surface area of a spheres by integrating of the small areas. Its small area can be expressed r squared sine theta d phi. So d phi, d theta is changing from the 0 to the pi. And the d phi is changing 0 to the 2 pi. And r squared sine theta. Then you could perform the calculations. It becomes 4 pi r squares. Maybe you have learned the area of a sphere is expressed 4 pi times r squares. We could calculate electric flux through a sphere. So we consider the charge of the Q is located at the origin. Then we could consider the spheres with the radius of the R. Every point on the surface of a sphere's magnitude of the electric field is expressed in these equations. And always the electric field is directed in this direction. And the areas is also has the same direction, ds. So if you consider the scalar product of the E dot ds, so E ds cosine 0. Cosine 0 is a 1. So this becomes exactly equal to E ds. E is always constant values on the every point on the surface. So you can multiply surface area of a spheres 4 pi r squares. Then you can substitute these quantities here. It becomes Q over epsilon naught. Then you could consider the larger spheres with a radius of the alpha r. Then we could same calculation. But again, in this case, electric field is 1 over 4 pi epsilon naught Q over alpha r squares. And this is 4 pi alpha r squares. You can find that the 4 pi is going to be cancelled out. Alpha r square is cancelled out. Then again, you have a same expression, Q over epsilon naught. So electric flux is independent of the size of a spheres. Then we'd like to consider the different charge is located at the origin. One case, we consider the charge of the Q. The other case, we consider charge of the alpha Q. Then calculate electric flux. In the case of this case, it's a capital phi sub E. It becomes Q over epsilon naught. But in this case, right hand side, phi sub E prime. It becomes alpha Q over epsilon naught. You can find a different electric flux due to the different charges. Electric flux is proportional to the magnitude of the net charge inside of the spheres. So we discovered this electric flux is independent of the radius of a spheres, but it's dependent on the charge inside of a spheres. Okay, this is the end of the first session.